part of today's lecture in CS 746 for February 10th. And this is on hypothesis testing. This is a specific kind of hypothesis testing known as A/B testing. Used by many social media companies, for instance, Meta / Facebook, Google, even X, formerly known as Twitter, all use data science and statistical methods to determine the best user interface. Under Wikipedia, we can look on there, we can find a pedantic definition. A/B testing, also known as bucket testing or split run testing or split testing, is a user experience research method. It's a way to compare multiple versions of a single variable, determining which one is more effective. These are links. If you click on these, when you download this, you can read an article about how we use A/B testing at Facebook. Or down here, you can click on this and read an article talking about how the way they use A/B testing at Facebook is flawed. And, it's a, we need to sign in. Okay. Yeah. And it starts off with a wonderful quote here, 37 words. Oh, and someone deleted it. Yay. Okay. The quote was something like, A/B testing is you're like forcing yourself to do a lot more work than you need to when you're doing A/B testing, is the point. So we may need to change those links around. Download them. Yes, I should have done that, huh? All right. Let's take a look at it. The simplest format, we select a single item to change. For instance, currently our website says this offer ends soon. So H0 is this is a good way to get people excited to go buy our product. B, someone says, why do we change this to offer ends at midnight tonight? We give them a hard deadline. I think we'll get more people that buy our product today. So our H alpha is this is better. The new way is better, right? So we want to test, we're not going to bother making a change if it's worse, right? So we want a one-tailed test. If it's better, we'll go with a new one. We choose a metric. Clicks, we're just trying to get social engagement. Purchases, are we actually Amazon? We're trying to sell stuff. Time spent on site, are we just trying to, we're like Netflix and we want people to be binging all the time, right? We choose a sample size. For some time period, long enough to reach that chosen sample size, we randomly offer option A to half of our visitors and option B to half of our visitors. So we just randomly present the page in two different formats simultaneously to different people, right? And so our theory is that by presenting it simultaneously to random different people, we'll get a nice unbiased result. Alpha and beta. We've talked about alpha already, but not beta. Again, alpha is the probability of making a type 1 error, incorrectly rejecting the null hypothesis. Beta is the probability of making a type 2 error, incorrectly failing to reject the null hypothesis. So for A/B testing, we want to try to find a way to minimize both of those errors. Right? We don't want to plug something in that's or ignore something that is a useful statistic. We want to make sure that we have enough data to prove that we haven't incorrectly accepted the null hypothesis. So here's again alpha and beta. Alpha is here, beta is here. H0 is true, but we rejected it. H0 is false, but we failed to reject it. So why? We want to detect our minimum detectable. How many samples do we need to collect? How long do we run this experiment for? By having alpha and beta, by choosing values for both of those, we can calculate how many samples we need to collect. And it depends on how far apart means are between the B test, right? As well as what levels of significance we use. So, we're going to choose, even if we have a two-tailed test for alpha over 2, we're going to still use beta as a one-tailed statistic. So if alpha is 0.05, then z of alpha is over 2 is z of 0.025 or 1.96. If we want a 99% confidence interval, alpha over 2 is 1/2 of 1% or 2.326 standard deviations away. If we choose beta is 0.2, we're going to do a one-tailed test. And again, we accept a higher error rate with beta, generally speaking, right? So here's our alpha and our beta. Here's our control value. Here's our B test, the new version buy at midnight tonight. Our offer ends at midnight. Here's our 1 minus alpha over 2. Where we're failing to reject the null hypothesis. Here's the means we're getting different. Here's the critical value we're looking for in our test, alpha over 2. And here, of course, now this is our beta in our 1 minus beta in our data set. So we're trying to graphically show you. So the minimum effect value statistic, again, our formula is, given this variance, given the effect size, the difference between the means we collect, right, the number of values we need to calculate, and this is our Z statistic here, is, or Z of alpha over 2, right? So is Z of alpha over 2 plus Z of beta over delta, the difference in the effect size, square that, multiply by the variance of the distribution, the known variance of our population out there. And that will give us a number, and that will tell us how many things we need to calculate. And you notice that, of course, that the effect size here is the denominator of the equation. So as we're collecting data, it might move. And we might see the size, the number of values we need to collect might go up or down, right? If we see a very small effect, we'll have to collect more samples. If we see a huge effect, we need to collect fewer samples. So the key point, Z of alpha over 2 and Z of beta are the numerator. High confidence requires more samples. If we randomize 50-50, we have to run that long enough to get in samples. If we don't run the experiment long enough, we'll do this, post this up later. I actually had some feedback from a previous GTA. He provided some of these wonderful PDFs about job interviews that he'd undergone and training for job interviews for data science careers. And one of those was a list of sample interview questions. And so they were asking, what happens if we end our A/B testing experiment early? And the answer is, don't do that. So validity threats. What can make our data be bad? First of all, we have that stable treatment, an assumption that one group does not interfere with another group, right? We don't think we have, Alice and Bob sitting next to each other in the cafeteria, and Alice is ordering the same thing as Bob is. They're looking at the website, and Bob says, hey, mine says by midnight tonight, where yours says offer ends soon. Huh, that's interesting. And they start talking about it. Now they've got a biased sample, right? Survivorship bias. If we have a multi-step process, we can draw conclusions from an incomplete data set based on the fraction of the data that survived. Classic example of this, World War II. They were trying to figure out what parts of the planes they needed to reinforce. And they started looking at the planes that were coming back. And they says, well, you need to reinforce this part of the fuselage. And someone pointed out that the planes that weren't coming back had to be counted in there too. And what they were seeing was these were the planes that hadn't been damaged in the most deadly parts. They said, we need to reinforce this other part of the plane, right? So sample ratio mismatch. If for some reason, we don't send out 50-50, or for some reason, there's a power glitch or something, and all the people we're sending B data to, get dropped out of our data set. We have an imbalanced data set. Primacy effect. Sometimes people don't like change. My wife this morning, they updated her iPhone, and she says, it's categorizing my email now. I says, is that good or bad? She says, I don't know. I haven't decided yet. Some people will immediately say, I will say, change, I hate it. It's evil, right? Because I'm a grumpy old man. So other people will be like, yeah, this is great. So this is a change of version. I don't like, you've moved my cheese. There's an old book, stupid management book about, mouse, and they can't find their cheese anymore. Anyhow, change of version. There's also called a novelty effect, the opposite effect. People see something new like, this is cool, this is awesome, and they all want to jump into it, right? So we can see our key performance indicators, right? We can see that they decline temporarily and then they come back. And that's an effect we have to, be willing to look for, right? Or we can have the novelty effect, temporary increase, because everybody's like, oh, this is exciting, and then it goes away, right? Obviously, if you say offer ends at midnight tonight, and then you keep offering it daily, people are going to start taking it seriously, right? So you have to do it on different things. Other effects to consider: day of the week. There are people, things don't happen as much on Sundays, maybe, right? The instrumentation effect, the fact that you've changed the web page, maybe it makes it load slower, and people are like, I'm frustrated, I give up. Right? It's not loading at all. Competition. Your competition can release a new product at the exact same instant you start running your A/B test, right? So you have to look at all these possibilities that can mess up your A/B testing. Now, is this serious or is this a joke? Imagine, this is the quote, this is a Twitter post. Imagine living your personal life such as you never took or allowed to take any action unless you could first quantify or measure its impact. Now you understand one of the pathologies affecting the tech industry. He's pointing out that Facebook was using A/B testing for literally everything, even when it didn't matter. We're going to move this button over, a few pixels to the right. Well, let's do an A/B test on it to see which one is better, right? So as Dario Gieselar in a post says, define what you want to do is you look at what your vision is, right? We're going to make it better by rearranging the user interface. We think we're going to have a significant improvement. Now you test whether your improvement that you expect to see is really happening or not, right? So you run the A/B test to validate your progress in reaching a large vision. The engineering problem of A/B testing. Let's see if this link works. Maybe not. Oh, okay. So here's our almost end of our slides. So this is our table for our error rates in here. We talked about true positive, true negative, right? If we look out there and say, how many of our values are correct and how many are incorrect, that's what we call the accuracy. True positive plus true negative over all of the answers we give, right? So we have a fraction of correct answers over all the answers, right? This is not the greatest metric to use when you're testing something. Precision and recall. Basically, this is testing how often your true positive, right, misses, where it misses the target. It says true positive plus the false positive. How often do I make a type 1 error? Recall, true positive over true positive plus false negative. How often do I make a type 2 error? This fraction tells me how often, hopefully I'm, my true positive rate, I only make a true false positive, 10%, I get a 90% value for my precision, right? The F score actually takes precision and recall and uses what's called the harmonic mean of those two values together, and gives you a single number that tells you how good your test is at not making either kind of error. Because after all, if you wanted to, you could have a test that says always reports true positive, right? And you would never, ever make a false negative error. If you always reported positive, right? You have a test. Does this person have COVID? Yes or no? The test always says yes. It will never, ever fail to find someone who has COVID. It will tell everybody that doesn't have it that they have it, right? So that's why you want to look at precision and recall. And of course, this is another term for recall. It's called sensitivity. And then this is specificity. True negatives over the true negative plus the false positive. So how specific are we at not telling people that they have it? We don't want to incorrectly make people think they have a disease when they don't. So that's our specificity we're looking for there. Okay, enough of that lecture. Now we're going to do a brief on the project. I think we've got all your project topics picked. and uploaded. We had a couple teams that were behind on that, but we've signed them. We had some teams that had a little bit of communication issues within the team, and they tried to pick two different topics. But right now, everything's settled. So it's time for us to share the data. So we'll be sharing the document folder in Blackboard tomorrow night. So keep checking your Blackboard this Tuesday night for your data and be ready to start messing around with it. Okay, it is 11:58. It's a pretty good time. I'm going to go ahead and stop recording. All right. So at this point,